Hello everybody, and thank you for having me. My name's Illya, I work for Codeplay, and I'm going to give you a talk on safety critical development in automotive cars. And I'm probably going to scare you silly. I don't know how many of you drive or want to drive in the future, but where I saw on the slides that you had earlier, you were talking about C++ 20 and 23. Well, in this land, they're still in land of pre-C++ 11, C93 and that. So concepts that you think are common day, probably not in their domain. But anyway, so talking about automotive, and before I go any further, you're probably why I have these Jenga bricks here. So I thought I'd add a bit of a variety to this talk, and what I'm going to do, if I remember, and maybe I want some audience participation, I don't know, every other slide or slide, I've got some questions I am going to ask you, and I would like you to answer them truthfully. And if they break a coding rule or a standard, I'm going to add a brick to that pile. Now, what I forgot to do was I forgot to bring in my little smart car model. So I would then build the stack and put the car on top. So hopefully by the end of this talk, if you all answer the questions correctly about what you do with your programming, there's hopefully not a very tall stack of bricks there. It should just remain at one. But I'm going to see what happens. So that's the impromptu bit to my talk. So, the first slide. Whistle-stop tour of safety critical development. This happens in automotive. They are, as I said, about 10 years up behind, just going to dual core. Wow. Multi-threading. I don't know about that. That's too hard. So basically they're trying to stay away from complexity. Anything that they can verify and keep safe, that's where they are. And they're slowly gravitating to all this kind of software that you guys think, well, is old hat, multi-threaded environments and stuff like that. So it's pretty mind-blowing. So, if I can get this slide working, this slide is the level of technology in a car, and it started off a few years ago about 11.0, so that's basically you in your mini miner just going around with a battery, that kind of technology. Then you move up to adaptive assistance and level 2. So present day with your car, if you were to buy a Volvo today, you'll be probably at level 2, level 3 technology with assisted driving aids. And you think, no, we're pretty smart. But by I don't know how they come up with this date. It's like marketing. It's totally separate from the actual development priorities. That's my programming aspect to it. But 2026, that's when we're going to have fully autonomous vehicles. Now, some of you might have already seen, like with the Uber and the recent accident in America where there's a fatality. Some cars are kind of approaching that already. They're even in the automotive industry talking about AI, and on one hand they want it, on the other hand it's so complex it scares them silly. And with all the constructs of C++ these days, and that's another aspect. I can't remember if I have in the slides Misra, but you guys might have heard of Misra, which is a coding standard in the automotive industry, and that is stuck at Misra C++ Guide 2008. So all the stuff you're probably writing probably will not pass because it's just not allowed. But yet they're trying to do this, you know. And in some ways I would say they're pretty successful. So it all boils down to Moore's law, basically. Up to a few years ago, the only thing they would have in their computer was a single core CPU, and they would just try and put everything on it. All the processes, all your media, all your communications and stuff. And they're all sit there, all partitioned off, no interference, so no one program can interfere with another, all verified on a single core, because it's the least complex sort of system. But they realised they're hitting Moore's law and they can't carry on going this, so they're going to have to go to a multi-threaded dual core, multi-core environment. And if they're going to go to AI, well, you can see where that's going. They're just basically not going to do it. So they're looking for alternatives. The alternatives are like what's already been happening in the games world, mobiles, on your phone and stuff like that. So I think it's time for my first question, since my phone has just switched itself off. Right. How many of you guys use recursion in your code? Oh, I think that's definitely a block. That's a no-no. Right, good. I like that. So, back in when the space shuttle first was constructed, there was about 5,000 lines of code. And that was a lot of code, and it all had to be verified. And up to a few years ago, Boeing, the 777, quite a modern plane, 3 million lines of code. But today, your car, or a new car, even in its present form, exceeds that 10 times over. And it's going to get worse, or better, depending on how you look at it. And the thing is, they're all using single core or dual core ECUs. So there's all these little ECUs planted around your car. And I was at a conference in Scandinavia, and Volvo were doing their old AI car, which they were doing semi-autonomous around Gothenburg. And they had all this communication network, and one of the things they hit was actually bandwidth going across the car. So they solved one problem, hit another. But anyway, so that's where it's all going. And these are all the gadgets that you all love. That's going, and this is by no means the list now. I mean, you've got aids in your car which detects when you're going to sleep. You've got line assistance, all kinds of bits and pieces, and they're all adding to the code base. The cost of a car nowadays is not the material cost, it's the software costs. As I said before, that's where it's all going, in your braking system. There's just emphasising the braking system, you've got time slots, so it's software. Your software must make a decision in a certain time period, otherwise brake, too late, crash. And also you can't have a program if you've got like dynamic memory. Dynamic memory is I know you would use dynamic, so I'm not going to ask you that question. But dynamic memory, you think on your PC it's fast enough in an embedded system. One system asks for some memory, another system has to wait. That could be a braking system. You don't want that waiting. So all these devices in your car, they've all got to be separated off, and different criticality levels. Braking systems pretty high on there, the criticality. Infotainment, well, if that dies, you might be a little bit upset. But the infotainment system might be in the same cockpit as your speedo and oil gauge and stuff. So even though they could have separate systems, you've got to make sure the display doesn't interfere with other critical systems. So it goes not just at software code level, it goes at the item level. Right, I think that's time for another question. How many of you, and I'm probably going to explain this pretty badly, how many of you, if you write an if statement, bury it with more logic inside the if statement apart from 1 Boolean test? Because you think it's clever. Or you want to save lines of code. Right, I see some hands. Right. How can I ask, how do you test that? Okay. So you've got your car, you've got all the systems on it, being tooled and manufactured. There's probably a rack system in the back of these cars. Magna Morelli in Italy had 7 PCs lined up in the back, and it had its own battery generator with a separate klunk switch. But you've got to get it to this, running at 5 watts, but still running pretty awesome. so they say. So that's the challenge. Besides the software challenge, it's getting the CPU grunt or the GPU grunt into something that fits in a small box, and it can't be fan assisted. It must be passive. So back in the old days, they would use C code, handwritten assembly, all bespoke, verified, checked off. Any changes goes back up to the requirements list and back down, which reminds me of another question. Documentation. How many of you write documentation? Oh, sorry. Okay. How many of you don't write documentation when you really think you should? I think that counts. Okay, another one. Who writes requirements documentation? Who doesn't?
We have done it once.
If you've done it once, that's good. But do you go back and rewrite your documentation having changed your code? Yeah. You do?
Well, not now.
I think that's another brick. Right. So back in the old days, not a few years, perhaps still even today, you'll get people writing embedded systems with hand-coded stuff because they verify it works. If it isn't broken, don't change it. But unfortunately, with the systems that are coming into the cars that I've just shown you, that stuff isn't going to deliver the stuff that as customers demand in their cars. So basically, it's just driving features in your cars. So we're going to this scenario. We've got libraries, we've got standard libraries, we're trying to get all kinds of shenanigans going on there. And so you can imagine just from simple assembly code, or it's building up into multiple layer code stack. I mean, there's even Google's TensorFlow in there being proposed. I don't know how they're going to make that safety critical, but because there's one idea was for an AI. How do you test that? I mean, it goes out the door, but it carries on learning. Would you hold a cat up into it in 3 years' time? So is this still a cat? No. You know, an MOT for AI. So we got a software stack, and that's only just one camera, perhaps. I don't know. You got zillions of this, and this whole stack. And we at Codeplay, we work a lot on this, and we're going, oh my god. So, and you probably work in your own systems and think, well, I've got a lot of software. I don't really look at it. I just use a library. It's a third-party library. It does what it says on the tin. I don't really care what else it does. So who does that? Right. Let's see what my next slide is. I'm probably going to repeat myself, but the reason what this slide is in here is because when you write some code for your car or a plane, and any of these functional safety standards, medicine, railway, process, nuclear, you've got to understand the behavior and tick off, you say it does what it says, to all the code. So if you get someone's third-party library, like the standard template library, and you may only use one container, like the list container or something, I'm sorry, unless you can tell me you use the rest of the code, you can't have it. You've got to either use the code or not use the code at all. That's one of the bugbears with this previous situation where you save yourself time. You don't have to write it. It seems to be optimal. You take it as it is, but in a safety critical environment, that is not good enough. You have to, or your team has to go through and verify it, all the code. And that applies not just to automotive, but all those systems there, including medicine and stuff like that. So there's lots of functional safety standards out there. Some of them are law, and some of them are not, surprisingly. The D0178C, avionics, that's for aircraft, that is law. The ISO 26262, the automotive one, which seems to be growing the fad game, that's actually not law. But the reason everybody's jumping on the bandwagon is because if you stand up in the court of law and say, why didn't you use it? I don't know, I didn't like it. Yeah, that's not good enough. You're going to be taken to the cleaners, basically. And we've also got cybersecurity. So, while all these look from a safe point of view, what will cause injury or death, cybersecurity is closely related to that. They're still working out functional safety standards for this kind of activity, and that's going to be combined in the future, but that is a big concern. So there's cybersecurity. You've seen all the ones about the Jeep being hacked and stuff like that, and the wipers going, and the fans going. But that might well cause an accident, so that's why it's concerned. And another aspect, how many of you just write code as fast as it goes and just use all the raw power without any consideration for what actually you might be using? Yeah, sorry, that's another brick. So that's a very important thing. I mean, all these, you've only got a 12-volt battery in your car. I'm sorry, you've got to keep all these systems going. Just have that brick in there. So, for instance, all your systems have got to survive when you crank the key. So when you go down to 6 volts, they can't just go. It's got to survive at 6 volts and then come back up again, and not go off. And that's on a winter day. So. My next slide. Let's see where we're going with this. So, as part of your requirements, you're not just do technical requirements. You have to look at your code and say that camera is going on your car. You have to look at it, all the situations where it could possibly fail, and if it does fail, what is the possibility of injury or death? And then based on the usage, it may be not critical, up to very critical. A camera pointing at you whether you go to sleep may be medium critical, but a camera judging distance from you to the car in front could be very critical. So it depends a lot on the scenario you use the item for. And this dictates, at least for the ISO 262 standard, functional safety standard, the sort of levels of rigor you apply to your code. Which actually there's one missing off there. On the other side of the A, there's one called quality managed, which means they're not put into any safety critical rigor, but you at least must go through a process of checks and make sure that you follow certain processes that you've established. Just basic quality. So basically all these functional safety standards are telling you to do what you should be doing anyway as a programmer. Just making sure you cross the T's and dot the I's. I think that's time for another question. Okay, how many of you review your code? Okay, don't review your code. Right, okay, that's another brick. So in a functional safety environment, or the safety critical project, depending on the criticality, at level A, for instance, you as the coder can have your colleague in your team look at your code and say, I agree with that, I don't agree with that, and do a peer review. At level D, you've written some code, you have to get a consultant in from outside and look at your code. It gets very expensive and very timely, and also that's the same with the documentation, your requirements, and stuff like this. So somewhere in between A and D, there's these levels of activities that you have to be performed or get performed on your system. So anyway, I've got to add this brick. Right. Looking precarious. So you have these at level D. In the other functional safety standards, they have either numbers, and this is the one that really gets me. In the avionics one, they have A to D, but it goes the other way. Why? You know, I mean, why not? If you're going to be standard, why not be standard? It makes things safer, right? No. We've got to change our letters back to front. So let's see where we get to. So those ASIL levels, at least for automotive, they're based on these three tables. And so on the far right, you've got if an item was going to die or stop working, what would be the injury level? And then in the middle table, you've got how probable would that event happen? And then this important one here is whether, if the event did happen, whether you as a driver can recover from the situation or get the car or vehicle into a safe state. So it's not only when your software fails, you have to write into your software alternative routes to bring it into a safe state and carry on working. You just can't let it die. I mean, you've got to write an application, oh dear, it's crashed, I shall reboot it. You can't do that in a car. You have to, if a system fails or something's a problem, you have to show in your design requirements how you're going to bring that code or that system into a safe state. So then maybe go, I mean, some of the cars nowadays have limp home. That's a similar type of thing that's happening there. Your car's gone into a critical state, it's gone into a limp home mode. So these come together. You look at the item and where it's going to be placed in the car and what environment it's going to be put in and what's the risk of injury. And then they form this table. And that's how it's come up. And the QM is the bit where it's just quality managed. There's no safety rigor. And then D, that's the top of the range. You can see there's not much in there, but so if someone comes to you, and this really bugs me, if someone comes to you, I would like you to write some software to a certain critical level, because that, like ASIL C, that's actually wrong, because until you've gone through the assessment of putting it in the environment and what it's going to do and the risks that are involved and then you can go and say what ASIL it is. So it's actually, when people come to you and say, I want something written to an ASIL level, that's a guidance, but that's not probably what it might not end up as. Just to put that in context, at Codeplay, we are writing libraries and stuff that we do not know where they're going yet. So that's allowed for in the automotive industry. That's called a system out of context. So I'm developing something to ASIL B or ASIL C, but really that's only a guidance. When it's finally put in the car or the vehicle, or the OEM, the BMWs and the Audis say this is what it's going to be used for, they're the ones who tell you what the ASIL rating is. So you're allowed to develop stuff out of context, but it doesn't actually get its full qualification until it actually goes in the car. This is from the ISO 262, and this is some of the requirements you would have to write your software to. And this, and you probably, if you can read that, that shows you how archaic it is, because they say limited use of pointers. And that's ASIL A up to D, and so they're suggesting at D, you really shouldn't be using pointers at all. How? I don't know. But that's what they're suggesting, and that question, see, there's the one, no recursion. You can't use recursion in ASIL D code. You're advised not to use it in your ASIL A code. So you can see where I'm going on this. There's a lot of rules and controls of what you can and can't do, and a lot of it is what you can't do. So this applies literally to your code at C or C++ level, with coding standards like MISRA applied on top of that to tell you even further what you can and can't do. But it's also at system level, the design, to the verification, what kind of verification methods you do. Now that's another question. How many of you don't write unit tests? Right, brick. In functional safety, you've written some code. You need to show someone that it actually does what it says on the tin. And basically also, you've written not only technical requirements, you've written also safety requirements. Safety requirements and technical requirements may be very closely related or separate. But if you write some code, that's easy. I've got a requirement or a safety requirement, it goes down to the code. I change the code. What safety requirements have I broken? And that's the hard bit, is getting the trackability back up. I mean, it's be hard enough to know what requirements you've broken. Your requirements may be through your unit tests, but you also need tests for your safety goals to be achieved. And the challenge is then writing the tests to show that your safety goals are being met as well as your technical requirements. So there's millions of these tables. No, actually, that's an exaggeration. There's lots of these tables covering all aspects of your system, of which can be hardware and software, and the processes that you use, and the kind of formal, semi-formal, and models. At ASIL D, you may need to represent your code in a model, whereas at ASIL D A, you can just write it in Word document. The reason they do that is because I'm speaking to you now. I'm hoping I'm speaking in correct English. I thought some of you may understand English slightly different, come from a different country or something. So your interpretation of my word may be slightly different. So if I give you some requirements in a Word document, you'll probably end up not quite writing all the same code. And that can add to problems. Whereas if I give you a mathematical model of the thing, you'll probably get it right, every one of you, because that's more succinct, but it's harder work. So, how deep is your love? So you're writing your application up here, and this is what I touched on earlier, but you've probably got all that lot underneath it. And this is what I was saying earlier. You've got to, if you're writing this, you've got to verify all of this too. Now, the reason that one might be as a slightly different colour is because you are allowed, if you write in a component type style, your code, and you've said to them, you've got it passed, functionally passed. If you do not change it, you can use it again. So it's good to write your system in that sort of like a component level, in small enough units to say, like, I've done this work already, as against one big monolithic program, which means if I change one line, I have to go through the whole rigor process again. That's really, really painful. I think I'm going to have to ask another question. Oh, right, okay, I like this one, because this one is always good. What is it called? Who writes their code in elegant, complex solution prowess? Prowess. You must use the latest techniques in C++, because I'm going to show my prowess in using C++. Because I can. My point with asking that question is from a safety functional point of view, you have other people in your team. And you have to better be sure they're all up to the same speed as you, and that you haven't written into your code any assumptions. Oh yes, they'll suss this out, they'll work this out. Because it's bad enough you coming back to your code 1 month, 2 years, 3 years later, let alone someone else looking at your code. Because in a functional safety project, this code has to be archived and saved for 30 years. So not only does the system have to come back alive, someone's going to be looking at it and crawling through it. And if they don't understand it, they quite easily point the finger at something and say, that's a problem. So while it's very elegant, and in my opinion, yes, you should write to the latest coding C++ 20 and 17, you have to remember that someday your code may end up in a critical situation So simplicity is king. Right, where am I? I think I'm coming near to the end now. So basically, we're trying to put this kind of software stack into that car, but we don't know what the hell's going on, really. So that's about the conclusion. I'm thinking about finished, but not so fast. The reason it's not so fast is because not only do you have to, at least for functional safety in automobile, you've written your code, but what did you write it with? Compiler. Is your compiler correct? Did you test your compiler? What are you going to tell me that the code that comes out from this end, that end is correct 100% of the time? So in functional safety in automobile, not only does your code have to be rigorously tested and verified, your tools that help you create the code have to be correct. And we had one instance in Codeplay where I was leading a team, and it was a GUI application. So profiling code, power profiling on a GPU. So it produces all these lovely graphs. Looks very pretty. Worst case scenario, but how do I know the graphs are correct? I mean, how do I know a peak is actually meant to be where a peak is? So I could be making judgments on what I should do to correct my hardware or my code based on the peak being in the wrong place. I mean, that's the kind of criticality is. So anyway, that leads me to my near the end of my talk. Tools, thank you. Oh God, I love this. Just one moment. Who uses implicit costs? Right, that's good. I like that too. Anyway, I could carry on building this brick up, this stack up a long way. Thank you very much for the talk. The point is, if I had brought my car, which I didn't, and I placed it on top of that stack, it may look pretty stable, but it wouldn't take much to any one of those elements come together. Bad day, Friday, wind's blowing in the wrong direction. Your system has failed and your car crashes. So hopefully something to take away from the talk. And yeah, thank you very much. Any questions? Am I allowed for questions?
Yeah.
Yeah.
You mentioned that you need to be very comfortable with your compiler and possibly verify that. Does that affect the kind of optimizations you can choose? Because some of those get really esoteric.
Yes.
Could you repeat the question?
So basically the question was, using a compiler, the different optimization levels and how the higher optimizer levels can affect what the code is written on the outside, out in the output. Yes, if you're allowed to use those optimization levels, as long as you can prove to someone that they're correct.
What about how they interact with each other?
If you can prove nothing untoward happens, you can use it. The functional safety standards, or at least for the automotive, doesn't stop you using stuff.
What do you tend to use there?
They're least complex. That's basically the rule. That's what's going to make your life easy, whether it takes you 10 years or 1 year to write your code, and the cost is how complex is your code and how am I going to test that complexity to make sure that what I have written is what I intend it to write in the environment it's going to live in. Is that okay? Yeah, thank you. Yep, I've got two here.
What's the expectation with sort of upgrading the software in cars these days? Do they ever get upgraded? Do they get upgraded when you take them in for service?
Okay, so
is stuff happening over the air?
So the question is what happens to software being upgraded in cars? That is a big topic in the automotive industry. You will see in the future over-the-air updates. Tesla are doing it. It'd be more common. In the past, I can't remember the manufacturer. They gave their update out on a USB stick. but that just threw wobblies to the cybersecurity guys because how do you know that's the right cyber security? You know, how do you know someone hasn't hacked a USB stick? So there's issues all over the place. So it's a good thing. It will come to like you need to go somewhere or have an update, but with like so much software in the car, over the air updates is going to be more and more common because any aspect of that car needs to be updated. You can't wait for your next service, otherwise you might die in the meantime. Yes.
Just curious, does it mean that, for example, all the versions of Linux are qualified for security safety or something?
All the versions of all the versions of Linux
qualified for security?
No. So what happens with Linux or something like that? It probably goes in the infotainment system because that's probably not going to cause you to crash unless you place the wrong song. I don't know. But the whole point is there are Linux OSs out there, very few, and they're probably very limited in what the capability of what they could do. So it's probably not the same. I'm not totally up to speed with that, but it's probably not the same Linux you've got on your PC. For that reasons, yes.
So when I was at university, we did a course on ADA, which was taught to us as like the go-to real-time safety-critical language. Don't know if you have any experience with it, but how does it compare writing a language designed specifically for safety-critical systems?
I did have a little experience with. So the question is ADA? Is it better, same, and what the comparison is with, I suppose, with C++? I have written some ADA in the past, and I agree with you. It's much more leans itself much more naturally to doing things properly, as against shoot yourself in the foot with C++. Unfortunately, nobody writes in ADA. Otherwise, this will be an ADA++. Conference. So that's basically the question. That's basically the answer. It's just people use C++. And now, and this is the thing that the automotive industry and other industries have to face, they're looking outside of their development processes for solutions because they don't have the capacity and time to deliver the solutions that you want in a car. So they don't have any choice. And then if you write it in C++, that's what we're going to have to bring in and verify. So that's the challenge. Yes. Yes.
I wonder if I'd ask your perspective on the wisdom or whether you get any benefit of bringing this sort of rigor to more general purpose applications.
Well, as I said earlier, all the functional safety standards is trying to do is make sure you should be doing what you should be doing anyway as a software developer. It's to catch all those glitches, those moments, which was I was too late moments. So basically, that's what it's trying to do. It really does go over the top. I'm quite a methodical person myself, and even I can look at the functional safety and go, "Oh my god!" It really does go, "Wow!" But really, what it's trying to say is, have you your requirements? Have you looked at the consequences? Have you got weighed out if it should fail? I mean, when I write code, and I expect if you write code, you always look at what it's going to achieve, what you think it's going to achieve. You never write it for when it's going to fail. You only fix it when it fails. So you don't write code to say, well, actually, if this failed, what am I going to do? You then may add an error condition later. But really, in your requirements, you don't write. You write your requirements and safety requirements first, and then write the code, because you then have the tests to verify that you backed it up with your requirements and tests. So it's basically enforcing good programming standards, basically. Yeah. Is that okay? Yep. Any other questions? Thank you.